Okay, so let me introduce Chrysa. So Chrysoula Stathakopoulou, she's a PhD, an external PhD student at ETH Zurich, but she's actually conducting her PhD at IBM. And her focus is on distributed protocols and generally on BFT consensus protocols. And this is what she will talk to us about today. So Chrysa, the floor is yours.
Thanks, Zeta. I will try to share my screen. Do I share my screen now?
Yes, all good.
Good. As Zeta said, my name is Chrysa, and this work I will talk about is conducted in IBM Research Zurich. I will present Mir-BFT, which is a high throughput and robust BFT protocol for decentralized networks. And it is a joint work with Tudor David, Matej Pavlovic, and Marko Vukolic. So it all starts with blockchain as an inspiration. And bear with me for a few seconds to give a brief background. We refer to the blockchain as a chain of blocks of transactions, such that each block consists of a number of ordered transactions. And the blockchain establishes a total order on these transactions. We can refer to it as a ledger. And now we need to introduce the second important component, which is a network of untrusted nodes. What we want is to have this ledger as a copy at all the untrusted nodes, so they can execute the transactions in the same order. And this makes important that the copy of the ledger they have is identical. Enter consensus protocols, which ensure exactly that the replicas of the ledger are identical. And that makes consensus the core of blockchain systems, but at the same time, it is a fundamental and very complex problem in distributed computing, which made it more interesting. And it is also very critical to the end-to-end performance for the blockchain system, because intuitively, the nodes cannot execute the transactions faster than they are ordered by the consensus protocol. And to give a little bit more motivation behind our work, it all started back in 2018 when we were evaluating the performance of Hyperledger Fabric. And we measured Fabric validation at above 4,000 transactions per second. And we realized that if we use as a consensus protocol in Fabric a protocol such as PBFT, which is a single leader Byzantine fault-tolerant protocol, this will drive the performance to very low throughput because PBFT does not scale well at all. Of course, by that time, we knew of some other notorious consensus protocol that scaled excellently to thousands of nodes. But unfortunately, Bitcoin comes with its own issues like very high energy consumption, non-finality, which is critical when we look at systems such as Fabric, and also, of course, very low throughput and high latency. Now, we wanted to keep the good attributes of PBFT protocol, which is finality, low latency, and high throughput, but make it scale to a higher number of nodes to accommodate a throughput higher than Fabric validation. And this is how we came up with Mir-BFT, a robust total order broadcast protocol with the highest throughput we're aware of in wide area networks, tested up to 200 nodes. And it is also suitable not only for permissioned blockchain systems such as Hyperledger Fabric, but also for proof of stake systems, such as, for example, Algorand, that run consensus in committees of this scale. A bit more formally, we want to solve the problem of total order broadcast in a set of n nodes. F out of them may be Byzantine and behave arbitrarily, such that n is greater or equal than 3f plus 1. We are working in asynchronous networks, which means that messages may be dropped, reordered, or delayed. But we need some synchrony for liveness, which comes after a global standardization time, which is unknown to nodes. But after this point, we assume that the network can be synchronous again. The problem of total order broadcast needs to informally satisfy 4 properties. First of all, agreement, that is, all correct nodes deliver the same transactions in the same order. Validity, which means that if we assume a set of clients to the system, the transactions that the nodes deliver come from one of the clients. Also, no duplication, that means that transactions are only delivered once. And of course, liveness, that means that every transaction which is proposed by a correct client needs to be eventually delivered by all correct nodes. And the metrics we are interested in are throughput, which we measure as the number of transactions per second the nodes can deliver, latency, which is the time interval from the moment the client sends a transaction until this transaction is delivered, and also goodput, which we define as the number of unique transactions per second the system can deliver. Please interrupt me at any moment if you have questions. Now we will look a bit more into detail in PBFT to understand why such single-leader protocols do not scale well. So PBFT orders transactions by broadcasting them through a node, the leader node, which we call primary. And then there are 2 phases where nodes exchange messages to agree on the assignment of the transactions to a sequence number, and then agree again to basically guarantee liveness of the protocol. Now, looking at this picture, we can quickly deduce that the protocol has quadratic message complexity, and that might lead us to think that this is the reason the protocol does not scale well. But if we look a bit more carefully, we will realize that since we have n nodes in the system, each node actually only processes a linear number of messages, not a quadratic. So that led us to investigate more why the system cannot scale well. And we quickly realized that the main bottleneck is the primary that needs to broadcast the large batch of transactions through a limited network, through a link with limited network capacity to an increasing number of nodes. If we simulate, for example, this behavior with 100 Mbps link connection, we can see that as the number of nodes or replicas in the system increases linearly, the throughput based on the number of bytes the leader can send through this link decreases inversely proportional to the number of the nodes. Now, one might think that this is easy to solve by minimizing the loads the leader has to send out. For example, such an optimization would be to send out only hashes of the transactions instead of the big transactions, and have the client send out the payload to all the nodes, or even gossip the payload. However, we can see that if we have the client responsible for disseminating the payload of the transactions, if the client is malicious, it can lead to a situation where the client makes only a subset of nodes aware of the transactions, or even only the primary, the leader. And then it is uncertain how the protocol can proceed, because that might violate the liveness of the transaction, that might lead the leader to be wrongfully accused, or we cannot even agree on the batch, depends on how the protocol proceeds. So we investigated a different way of scaling the BFT protocols, which should be intuitive, because if you think about it, when we add more nodes to the system, we also add more resources. So it is not reasonable that by adding more nodes, the system behaves worse. And if we look at how PBFT works, we can see that we make the primary struggle, but at the same time, the other nodes have resources that remain unused. So we decided to use those resources and make all nodes behave as leaders. This can be very easily done by deterministically distributing the blocks to all nodes and having its leader lead certain blocks, so that at the end we have a unique total order of blocks. And the question is it as simple as that? Are we done yet? Unfortunately, or fortunately for the interest of this research work, the answer is no. The main challenge we have to tackle when we look at multi-leader or parallel protocols is request duplication. Namely, remember that the client wants to guarantee liveness of their requests, so the client cannot depend on a single node as a leader to propose their transactions. Instead, the client might want to send their transaction to more nodes. And if we have nodes being leaders at the same time, that might have as a result the same transaction being included in more than one blocks. Of course, it is very easy to handle the duplicate requests when we have a total order at the end with a very simple rule, such as, for example, only keep the transaction that appears in the block with the lowest sequence number. However, the damage is done because we have already wasted the precious network resources for more than one nodes to order the same transaction. And this is the main problem Mir-BFT tries to solve. Prevent duplicate transactions before ordering while still maintaining liveness for the transactions from correct clients. So the main principles of Mir-BFT are the following. We have multiple leaders, as we saw, and we shard the sequence numbers of the blocks through all the leaders, but in the end, we multiplex them in a unique total order. We prevent request duplication by having a rotating assignment of requests to unique leaders. We built the protocol on top of PBFT with some security optimizations that came in Aardvark protocol, for example, using signatures instead of max because there are some known attacks there. We also introduced a few optimizations. We parallelized network implementation, which is specifically important when we look in wide area networks, because in wide area networks, a single, for example, TCP connection between a pair of nodes can have very limited bandwidth. So we allowed the nodes to open multiple connections to take advantage of the whole bandwidth capacity of each node. And we also introduced a signature verification sharding optimization, which we will look into a detail a bit later. Now we'll get a bit more into detail on how Mir prevents transaction duplication with the rotating assignment I mentioned earlier. So what we do is we take a hash function, some hash function that partitions a domain in subdomains. We refer to those domains as buckets. And we use the hash function to map each transaction to a bucket. And then we assign a different bucket. We assign to each node a unique bucket out of which the nodes can propose requests. Now, for example, assume we have client request number 12 that maps in the blue subdomain that means that maps in the blue bucket, for which blue bucket the first node in the picture is responsible. And imagine we have transaction 13 that maps to the gray bucket for which the third node in the picture is responsible. Even though the clients may send the requests to more than one nodes at the same time, only one node is deterministically responsible for this request. So only one node will put this request in a block. Now, you can immediately ask what happens if the node responsible for a certain bucket is malicious or this node crashes. To guarantee liveness in this case, we periodically rotate this bucket assignment. So after some number of blocks which is configurable has been ordered, we rotate the bucket assignment such that some other node is, in this example, responsible for the gray bucket, and that the request will be eventually proposed by the other node. Now, the leader set can shrink or grow depending on whether the nodes are correct or not. In particular, we want as many nodes as possible to be in the leader sets to maximize the throughput of the protocol by maximizing the available resources to leaders. However, if there is an error, we go from a stable epoch where all the nodes are leaders to a recovery epoch where the number of the leaders is reduced, trying to keep out of the leader set the nodes that crash. When we enter a recovery epoch, we have bounded lengths of epochs. The epochs last for a certain number of sequence numbers. And if everything goes well during this epoch, we try to grow again the leader set. If, however, something goes wrong again during this epoch and it does not go through the end, we shrink the leader set even more. I earlier referred to also a signature verification sharding optimization. We introduced this optimization because as we tackled the network bottlenecks that were introduced from the single leader bottleneck, we soon discovered that signature verification becomes a bottleneck to performance, and we wanted to boost performance a bit more. And we realized that when a client sends a signed transaction, such that the leader responsible for this transaction verifies it and puts it in a batch and broadcasts this batch to the other nodes, what happens normally is that all nodes verify that this transaction is signed correctly. However, we don't need all the nodes to verify the signature, since we have an assumption that at most F of the nodes are malicious. So if we only have F+1 of the nodes verify the signatures, we can still be certain that the transactions is signed correctly. Therefore, we deterministically assign to each block a set of validators and ask only the validators to verify the request signatures, such that each time within the set of validation of the validators, there are F+1 nodes. Now I will talk about the performance evaluation of the protocol. So if you have any questions pertaining to the protocol itself, it might be a good point to interrupt and discuss. Okay, I will continue and maybe we'll discuss later. We evaluated the protocol using IBM soft layer in a wide area network we use 16 data centers spread across the world in all, not all, but in 4 continents. The machines we used were equipped with 32 virtual cores and 32 gigabytes of RAM, and they had the network connection limited to 1 Gbps. We evaluated the performance of the protocol for up to 100 nodes, and we use the payload for the transactions of 500 bytes, which is comparable to the Bitcoin transaction. And we also evaluated the protocol using larger transactions, 3.5 megabytes, which are the typical size of a Fabric transaction. We also evaluated the protocol on local area networks with the same number of nodes and the same type of machines. And we compared Mir-BFT first to single-leader PBFT protocol. We compared to chain, which is an optimistic protocol that very efficiently only sends its block to one node until there is a chain of passing the block from one node to the other. We also compared to Honey Badger, which is yet another protocol with parallel leaders, since it's an asynchronous protocol and it cannot have a specific leader. And we also compared to recent hot stuff. So first, let's have a look at the wide area performance, wide area network performance of the protocols up to 100 nodes. We can see with the gray line that PBFT indeed behaves as we introduced earlier and very quickly drops in throughput, inversely proportional to the number of the nodes. The chain protocol is behaving very nicely, but it is limited by the available throughput in the wide area net. It's limited by the available bandwidth between each pair of nodes in the wide area network, and therefore it cannot reach the highest possible throughput. And the Honey Badger, due to the heavy cryptography that is introduced because of the asynchronous assumptions, does not perform as well. On the other hand, Mir-BFT scales nicely up to 100 nodes, having a throughput above 30,000 transactions per second. And if we introduce the signature verification optimization, the performance boosts even higher. Now we still see the Mir-BFT performance dropping, but we realized that this is because in a wide area network, not all the machines behave the same, and the performance is limited by the performance of the slowest leader in the group. Looking at the latency of the protocols, we can see that all the protocols basically have in a wide area network latency in the order of 1-2 seconds. And it is also interesting in this plot to look the cost of introducing rotation to Mir protocol, which means how to make the protocol live. If we have Mir-BFT without rotating the bucket assignment, we can see that it is a little bit better in performance than Mir with the rotating leader assignment. But still the difference is not big, and this is also depending on the length of the epoch. So if the epoch is smaller, the impact of the rotation, if the epoch is larger, the impact of the rotation is smaller. We also compared to hot stuff. The implementation we had of hot stuff did not order the transactions, but as I showed earlier, it only optimistically ordered the hashes of transactions, and also did not validate signatures on transactions. So we found this interesting, and we wanted to compare Mir behavior in this setup. And we realized that even when the leader is broadcasting the minimum data pertaining to a transaction, such as a transaction hash, still after the number of nodes increases, the performance of the protocol drops importantly. In local area network, the chain protocol performs very nicely because the available bandwidth between its pair of nodes is now higher. But as soon as we introduce signatures to chain protocol, which are not there by default, we can see that computation makes the protocol in the purple line have lower performance. Mir-BFT with signatures and the signature verification sharding optimization scales very nicely in a local area network without without important differences between the machines in the leader group. And of course, PBFT, as we already knew, does not scale at all. Now, a very important aspect to look at is the impact of duplicates on throughput. We evaluated Mir with and without the duplication prevention mechanism. Namely, we removed the buckets from the protocol and evaluated how the protocol would execute if its leader would just order any transaction the clients would send them. And it soon becomes evident that the throughput suffers by the duplication. So with a gray line, we evaluate the protocol when the client sends the request to F+1 node, which is the bare minimum to guarantee liveness. And with the black line, we evaluate the performance of the protocol when the client sends a request to all nodes. And since now each of the nodes has to basically order all the transactions, the protocol behaves again like PBFT. Now, in the beginning, I said that the protocol is robust, so I have to justify myself. And one use case we looked at is how the protocol behaves when the nodes censor requests. And it is interesting to see that the bucket rotation mechanism does not introduce very high tail latencies. So to be more specific, in this experiment, we have 16 nodes across, again, 16 data centers with 500 bytes of requests. And we assume that an increasing number of Byzantine leaders drop requests from the clients. We examine the case where the nodes drop all the requests, the Byzantine nodes drop all the requests, 100% censoring. And we also examine the case where the Byzantine nodes drop random 25% of the requests they receive. The bucket rotation mechanism means that a request needs to wait a rotation before it has a chance being assigned to another leader and being ordered. So we expect by increasing the number of nodes that drop transactions to see the average latency increasing a bit. But even the 95 percentile latency is still in the order of a few seconds. And on the right-hand side, we can see the CBF of latencies in the worst case, where all 5 Byzantine leaders drop 100% of the requests. I should also mention that for this experiment, we had a random assignment of the 5 Byzantine leaders across the 16 nodes, repeated again and again and averaged out. Of course, the tail latency latencycycycy depends on which are the Byzantine leaders, because in the worst case, the Byzantine leaders can be the one after the other, which means that the request must wait, in this case, 5 rotations until it is ordered. But another interesting parameter that we examine in the paper is what happens when the epoch is shorter. And in this case, the performance of this protocol drops marginally, drops very little, but the tail latencies drop significantly. Finally, let's look at the wide area network scalability of fabric size requests, which is what we wanted to achieve with this protocol in the first place. So again, with the red line, I have fabric validation throughput as a reference, and gray line represents PBFT, and blue line represents Mir, here without the signature verification sharding, which is not important because network is the bottleneck and we do not reach computation bottleneck. And we can see that Mir-BFT in wide area network achieves about 8,000 transactions per second, way above the fabric validation bottleneck. Again, the protocol performance drops as we introduce nodes, since we introduce nodes that are not equal, even though in a cloud deployment, you ask nodes that behave the same, you cannot actually get them. So the protocol always behaves as slow as the slowest node in the leader set. In the local area network, that we have a better chance with having equivalent virtual machines, Mir performance is even better, and reaches 30,000 transactions approximately on 100 nodes. And this concludes this presentation. We achieved our goal of scalability to 100 nodes. We have the best performance of BFT protocol we are aware of in wide area networks and are robust to performance attacks. This protocol is being integrated as a BFT library to Fabric, and there is an active implementation of the production-ready Mir-BFT on GitHub. And finally, the paper is on archive. Thank you.
Thank you, Chrysa, for the great talk. So does anyone have any questions?
Yes, I have a question.
Yeah.
Does your SVS scheme compose with existing protocols? So for example, can you compose SVS with PBFT or hot stuff? And then if you do that composition, how do these protocols perform as compared to yours? So the question is that optimization, the SVS, something standalone that can be composed with other protocols, or does it depend on the way Mir-BFT works on the consensus level?
Actually, it is independent because it has to do with the signature verification on requests and not on the batches. So let me go back. The critical aspect of it is that we want a quorum of nodes to verify the signatures, and we don't need all the nodes to verify on signatures that would usually do in a BFT protocol. So as long as we exchange an approval, if you like, that the request is signed, this can apply to other protocols as well. For example, in hot stuff, the leader would broadcast the block, and the followers would send their signature share on the block only if the if they had verified the signatures in the block. Again, we can have a set of nodes performing this verification, not all of the nodes, even though in the hot stuff protocol, normally they are not assumed signatures on the requests, but in principle, yes, you could do that.
Thank you.
Okay, I can ask a question. So can you explain to me what happens if the client is malicious, for instance? Does this affect somehow distribution of the requests to the buckets and this process generally?
Actually, I hid the assumption that for the protocol to have optimal performance, we assume that this hash function, let me go back. So here we say that we take advantage of the bandwidth that is available to all the nodes. And this assumes that there is a uniform distribution of load on all the nodes. Otherwise, we wouldn't achieve the optimal performance. Now, we use a hash function for this because the hash function with a good hash function would indeed uniformly distribute the requests to the leader buckets. However, if the clients can play with what they put in the transaction, they can bias the output of the hash function. And we tried to resolve this by the format of the request the client sent. I don't have a slide on this, but the client request format contains the transaction, the operation the client wants to perform, the client's identity, that can be some ID or some public key, and a sequence number pertaining to the client. And the client can send requests within a watermark of sequence numbers, such as that the client cannot arbitrarily choose how the request would hash. And the protocol can limit the client watermarks even to 1 per client to prevent the client from basically messing with the distribution of requests.
Okay, thanks.
May I ask something?
Sure.
Thanks for the very nice talk. Very interesting. I have actually many questions because this is an area that you know, always, although I try to study it, always puzzles me. Okay, so let me ask you, because you are probably the right person to ask, since you have
Nice.
been involved with both the theory and the implementation. So first, I wanted to ask the assumption, the 3F+1 assumption of this comes from the standard consensus protocols, right?
Mm-hmm.
Which are information theoretic. They go for information, for perfect security, right? I mean, you said something about signatures at some point. So if cryptography signatures are used, then I think you can do better. You can do with you know, even half, even just a majority. So
yeah, actually, it I don't remember by heart all the different bounds, but it indeed can be done better with signatures, but it affects the number of rounds of the protocol. So in order to have a constant round in the protocol, a constant number of rounds in the protocol, like here 3, for example, it is shown that this is the optimal bound.
Okay, okay. So this comes from the PBFT protocol, right?
Yes, there are other protocols with, for example, linear number of rounds that have different trust assumptions.
Okay, okay.
May I add something? I'm not sure,
Yes.
but it has to do with also synchrony and asynchrony, because she wants security and asynchrony, and I think this is not possible with NHAF. Not perfectly sure, but this is something I recall.
Okay, okay, yeah, good. This makes sense. Yeah, we can all have a better look, definitely. And the other thing is, can you say again, or in a bit more detail, how the leaders are chosen? So what? Who chooses the leader? The leader or the leaders?
There is. We assume that there is a primary, which is the epoch primary. And if everything goes well,
sorry, this is an entity, right? Someone
one
is
of the nodes. One of the nodes, for example, or it could be an entity. Yes.
Yeah, right. And who decides who is the primary?
Well, this is orthogonal to the protocol, but the simplest solution, which is what we implemented, is to rotate the epoch primary in a round robin way around the nodes. Normally, if there are not faults during the epoch, we have all the nodes automatically included in the leader set. If we have faults and we have an epoch change, this primary is responsible for executing the epoch change, and the primary also reliably broadcasts the new epoch configuration containing the new leader set of the new epoch. I think I cannot hear you anymore.
Yes, yeah. Okay, thanks. Okay, there's something in the chat, right? Okay, comments on the same thing, right?
Is it something in the chat? I cannot.
It's just a discussion because Puran remembers the impossibility that says that in asynchrony and Byzantine adversary, you cannot have more than F out of the F plus 1. So yeah, it's you can do better. You can do a half, for instance.
Where is the chat?
What we discussed before, I don't think you can see it.
Signatures.
Yes, you have to stop sharing.
Aha.
Yes, so I think you can see it, but it doesn't matter. It's just on this.
Okay. Yes, please relay anything.
Yes. Chris, I have another question now that came to mind. Can you go to this graph that you have with the throughput and the comparison of the different protocols? I think it was the first graph that you showed.
I can move faster. Good. Yep.
Okay, so I think, so my question is, I'm looking at this chain protocol, and it goes straight, and it seems like if you go to more nodes, it will continue going like a straight line. So it has a constant throughput. And then you have Mir that drops and then goes almost like trying to go straight. But the question is, if you evaluate it for 1,000 nodes, will the communication complexity be the bottleneck for Mir and it will drop while this chain doesn't have that problem? How do you predict that it will look? I'm not sure.
Chain has a nice thing that it has constant communication complexity. As a matter of fact, it has communication complexity of one message. Because the protocol works as follows. I am the leader and I pass the block to you. then you pass it to Dionysis, then Dionysis pass it to Lyoba until the protocol makes a full, until the block makes a full round among all the nodes. It has very high latency, yes.
Okay.
That's the catch in chain protocol. Otherwise, it has very nice, it has the best possible throughput, actually.
Okay, but that's cheating, essentially.
It is an optimistic protocol because once a fault occurs, you cannot use it anymore. You cannot guarantee liveness, and you need to, actually this protocol then falls back to PBFT.
Okay.
Where we compared suites to see how we compare to the best there is, like the best possible solution. And an interesting observation we made is that if we don't increase the number of parallel connections between the nodes in a wide area network, even if you have this optimal performance, you cannot reach the highest available bandwidth because you do not exploit the whole bandwidth. Because if I just send one message to you and the wide area network has gives us, for example, 5 Mbps, regardless if I have 1 Gbps available, I cannot take advantage of it.
Yeah.
And this is what happens. I mean, we observed it in wide area networks. And then we introduced this parallel connection optimization, which is important though in protocols with higher message complexity only for few number of nodes. Because once the number of pairs increases, it's not really important if the available bandwidth per pair is small, since there are many pairs and we will end up using the whole bandwidth. Then the reason we believe, so there are many reasons Mir performance is not perfect. Once we started implementing the prototype, we have run into many issues, such as contention in threads when reading the requests, contention in threads when processing the blocks. And I am very much convinced scalability at this throughput is a matter of implementation skills. Because it is such a high the number of transactions from the client, not the messages, the blocks you need to process, but the requests from the client are so many that it is challenging to process them while maintaining a high throughput. Then when the nodes start not behaving as good as expected because they are virtual machines, we observed that they don't finish their epoch at the same time. So at the end of the epoch, we need to wait for the slowest guy and then move to the next epoch. And the more nodes, the more slow guides we probably need to wait for, and the worse the performance is in the end.
Is this why you changed the leader set? Like you're trying to keep the fastest?
Yes. If the performance is so bad that in the end it causes a view change, we will kick this node out of the leader set and keep the fastest guys. Yes.
Okay, two questions that come from that. The leader set is broadcast by the, do you do reliable broadcast from the primary for the leader set to the rest, right?
Yes,
okay.
yes.
Another thing, on this plot, the experiments are like optimistic, right? There are no crashes, there is nothing, no faults.
Right, yes.
Okay.
But we had one experiment, but it was not a nice slide to show. Wait. Where we actually tried to have a straggler. We introduced a straggler that would delay the blocks in a wide area network, such that so the Straggler is trying to affect the protocol as much as possible. So the Straggler is trying to reach the epoch change timeout as much as possible. And as soon as, just before the epoch timeout, the Straggler was sent out the block. So in this experiment, we had an epoch change timeout in 20 seconds. And we had the Straggler delaying their blocks 15 seconds. So the Straggler would try to, if we increase the time the Straggler tries to delay the blocks in this experiment, it is detected immediately. And well, when we reached 15 seconds, there were few blocks before the Straggler was detected. And once the Straggler is detected, we have an epoch change. It is kicked out of the leader set from the primary and remains out of the leader set until a round robin rotation in epochs leads the Straggler being actually the primary. Then the Straggler would put, assuming that it is a malicious node. If it is not a malicious node, it would not put itself back. But if it is a malicious node, it would put itself back in the leader set. And this would start again, over again and again. And we observed over the whole round of epochs a drop from 24.8 to 18,000 transactions per second, which is not terrible.
Yeah. Okay. Thanks.
Sure.
Any other questions?
If no one else has a question, I have one more regarding your policy of packet allocation using the hash. And this is following up on your remark that you base your construction on the uniformity of the hash function. And you mentioned that one of the ways that you avoid a client overloading one of the buckets, biasing it, is by limiting the amount of different data that it can put in the hash input, but by limiting its window of sequence numbers. And one question I had here is, does this assume that the set of clients is closed? So do we know their identities and their fixed public keys? Or because otherwise I could create a new client, pretend to rejoin with a new key and so on, and simple attack the scheme. So is this assumption underlying here?
You're correct. Yes, we have this assumption. However, even if you civil attack the scheme, there will be some poor clients that are delayed. Well, the worst thing you can do is try to send all of your requests, for example, to one bucket, and make sure that the distribution is not equivalent anymore. But like this, you will mostly delay yourself. And if there are some poor clients mapped to this same bucket, it is equivalent. We can think it as an equivalent of the bucket censoring those requests. So I believe that we would experience a similar behavior as the censoring experiment I showed earlier.
Yeah, that makes sense. Thank you.
Sure.
Okay, are there any last questions? We're almost at time. Okay, so if not, then Chrysa, thank you very much for the great talk and for answering all questions.
Again, thank you for inviting me.
Yeah, of course. And then see you all next time.
Good. I will try to be here next time. I'm curious.
Thank you so much. Have a great day.
You too. Bye.